Okay, so now we're going to work a few examples of RC and RL circuits, specifically first order circuits, for the voltages and currents present in the circuit. And we're going to use, again, the general form that I mentioned in the last video. So for example, here's an RC circuit with 3 resistors and a capacitor. I've got an initial condition provided that's non-zero. So the capacitor is charged up to 10 volts. Presumably there has to be another configuration with an active source in there to be able to do that. But we've charged the capacitor to 10 volts and then connected it to these 3 resistors. And we want to find the voltage Vx across the 12 ohm resistor. So in general, we do a few things. One, we need to find the time constant of the RC circuit, tau, which is given as the equivalent resistance seen by the capacitor times the capacitor. Step 2, we're going to find the expression for the voltage across the capacitor, which we know is A e to the minus t over tau plus some final condition. And again, since Vc at time 0 is what we termed V naught, the initial condition, this equals A e to the 0 plus Vf. Therefore, A is V naught minus Vf. So this expression that we're looking for looks like V naught minus Vf, where V naught is the initial condition, Vf is the final condition, times e to the minus t over the tau that we find in step 1, plus the final voltage. Okay, so for part 1, we're going to find the time constant, tau, which is equal to the equivalent resistance seen by the capacitor times the capacitor. So we need to redraw the circuit from the point of view of the capacitor. So to do so, we pull out the capacitor, so it's open circuited, and we draw the remainder of the circuit. And we're looking at the equivalent resistance seen on the terminals of the capacitor. And hence is our equivalent circuit. So we see that the 8 and the 12 ohm resistors are in series, which makes 20. And the 20 ohm resistor is connected to the same nodes as the 5 ohm resistors, thus is in parallel. So our equivalent is 20 in parallel with 5. Which equals 4 ohms. Therefore, tau is 4 ohms times the capacitance of 1.1 farads, or 0.4 seconds. Now, part 2 is to apply the general expression for Vc, which is the capacitor voltage. Note we always find the capacitor voltage first in RC circuits, regardless of what we're asked for. In this case, we're asked for Vx, which is across the 12 ohm resistor, but we need to find Vc first. That's the unknown that everything else depends upon. So Vc is again equal to V naught minus Vf e to the minus t over tau plus Vf. So we need to know the boundary conditions. Now, one of those was given to us in the beginning of the problem, that V naught, which is what Vc at time 0 is equal to, is 10 volts. So what about the final condition? Well, the final condition in this problem must be 0 volts, and that's because we can identify that there are no sources in the problem forcing the final value to be anything else. The forced response is just 0. So this is, in other words, just a natural response problem. But if you don't identify that directly, again, just apply it to this equation. So that equation resolves to 10 e to the minus t over 0.4 plus 0 volts, or 10 e to the negative 2.5 t volts. Okay, so now we're back at the original part of this problem, but now we know the value of the capacitor voltage Vc. It's a known, and that's this function, 10 e to the minus 2.5 t. So now the objective is to find Vx. This is where we use the skills that we learned in the previous part of the course. So we're going to use whatever technique we want to find Vx. I will use a basic voltage divider since I know for example, if I create a ground here, this node is just VC, which is a known. Vx is going to be a fraction of VC based on the division through the series path of the 8 and the 12. So I could write Vx as a function of time equals Vc as a function of time times 12 over 8 plus 12 as being my voltage divider expression. You could solve for Vx using a KVL of that loop. You could do nodal analysis, whatever you would like to do. So finishing this out, I get 10 e to the minus 2.5 t times 12 over 20, which equals 6 e to the minus 2.5 t volts.